Have you ever looked up at the night sky and wondered what secrets the universe might be hiding? What if I told you that the answers to some of our most pressing challenges here on Earth could be found not in laboratories or textbooks, but in the far reaches of space? It's easy to think of space exploration as something detached from our daily lives, a pursuit of distant stars and alien worlds with little connection to our own. But the truth is far more extraordinary. Every discovery, every mission, every glimpse into the cosmos brings back knowledge that could revolutionize life as we know it. Today, we're setting out on a journey through 30 of the most groundbreaking space discoveries, findings that could reshape everything from the technology we use to the medicine that saves lives, to our very understanding of our planet's place in the cosmos. This isn't just about distant galaxies or theoretical physics, it's about tangible, real-world transformations. Imagine a future where diseases are cured using insights from studying extreme environments in space, where energy is harnessed more efficiently thanks to solar innovations tested beyond our atmosphere, or where climate change is better understood by observing Earth from afar. These aren't far-off dreams, they're possibilities being unlocked right now by the relentless curiosity of scientists and explorers. So join me as we dive into mysteries that bridge the vastness of space with the intimacy of our everyday existence. Together, we'll uncover how the universe's most astonishing revelations are quietly rewriting the story of human progress, offering hope, inspiration, and perhaps even solutions to the challenges we face right here at home. This is more than a countdown, it's an invitation to see the cosmos not as a distant frontier, but as a partner in shaping our future. Our first discovery takes us to the red planet itself, Mars, and a revelation that fundamentally alters our perception of it. For centuries, we looked at Mars as a dry, dusty, and apparently lifeless world. But that view was shattered with the confirmation of what scientists had long suspected. Liquid water isn't just a relic of Mars's past, it's present there right now. Using ground-penetrating radar from orbiters, researchers detected a massive subsurface lake buried nearly a mile beneath the southern polar ice cap. This isn't a small trickle or a damp patch. We're talking about a body of water estimated to be about 12 miles across. And where there is persistent liquid water, the fundamental ingredient for life as we understand it, the possibilities become incredibly exciting. This discovery is a monumental leap for the future of human exploration. Water is the key to survival off-world. It's not just for drinking. It can be split into hydrogen and oxygen to create breathable air and rocket fuel. The prospect of a readily available water source on Mars drastically reduces the immense cost and risk of ferrying all those vital supplies from Earth. It makes the dream of establishing a permanent, self-sustaining colony on Mars move from the realm of science fiction into a tangible, achievable goal. We could literally use Martian water to power our journey back home. Beyond its practical use for astronauts, this Martian water holds profound lessons for our own planet. By studying the history of water on Mars, how it once flowed freely on the surface and now exists only in hidden reservoirs, we get a mirror into Earth's own past and potential future. It helps scientists model climate change extremes and understand the delicate balance that allows a planet to hold onto its oceans over billions of years. Mars serves as a stark warning of what can happen when a world loses its protective atmosphere and life-supporting systems. But the most tantalizing question of all is whether we are alone. That subglacial lake on Mars is likely extremely cold and salty, a harsh, briny environment. Yet here on Earth, we find life thriving in exactly such conditions, in the dark depths under Antarctic ice sheets. If life could arise independently in two different places within our own solar system, it suggests the universe might be teeming with biology. Finding even simple microbial life on Mars would be arguably the most significant scientific discovery in human history, telling us that life is not a miracle unique to Earth, but a natural part of the cosmos. This single discovery on our planetary neighbor opens up a new chapter in our quest to understand our place in the universe. Moving from the familiar deserts of Mars to the staggering diversity of worlds orbiting distant stars, our next discovery expands the search for life to an entirely new scale. For most of human history, we could only wonder if other planets existed beyond our solar system. Today, we know of thousands. These exoplanets, especially those found nestled within what scientists call the habitable zone of their stars, represent one of the most profound shifts in our cosmic perspective. The habitable zone, often poetically nicknamed the Goldilocks zone, is that narrow orbital region where conditions are just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. And water, as we just learned from Mars, is the universal prerequisite for life as we know it. The methods used to find these distant worlds are feats of ingenuity in themselves. Astronomers don't typically see these planets directly. Instead, they detect the subtle shadows they cast as they transit in front of their host star, or they measure the tiny gravitational wobble they impart, pulling the star ever so slightly back and forth. Each discovery is a triumph of precision and patience, but the real magic begins after a planet is found. Using powerful instruments like the James Webb Space Telescope, scientists can now analyze the light filtering through an exoplanet's atmosphere during a transit. They are essentially taking a chemical fingerprint of an alien sky, searching for the telltale biosignatures, gases like oxygen, methane, or ozone that, in combination, could strongly suggest biological processes are at work. This search for life beyond Earth is undeniably thrilling, but the implications for life on Earth are equally transformative. By studying the atmospheres of these distant worlds, we are essentially running a grand cosmic experiment in climate science. We can observe planets that are runaway greenhouses shrouded in thick layers of heat-trapping gases and see a chilling possible future for our own world. Conversely, we might find stable, temperate planets that have maintained their balance for eons, offering models for long-term climate stability. This comparative planetology gives us vital data to refine our own climate models, helping us better understand the complex interplay of atmospheric chemistry, stellar radiation, and planetary cycles. It provides a universal context for our own environmental challenges, showing us what's truly possible within the laws of physics. The discovery of a truly Earth-like world, with an atmosphere rich in oxygen and signs of liquid water, would be a monumental event in human history, fundamentally altering our understanding of our place in the universe. It would suggest that the ingredients for life are not rare and precious, but perhaps common across the galaxy. This knowledge could unite humanity with a shared purpose, fueling a new era of exploration and innovation aimed at one day reaching those distant shores. While the journey to an exoplanet remains a challenge for future generations, their discovery today gives us something equally valuable: hope. It expands our vision of the future, offering not just a mirror to understand our own world, but a map to countless others, reminding us that our horizons are limited only by our curiosity. While the hunt for life on distant exoplanets captures our imagination, some of the most critical clues to life's origins might be hiding much closer to home in our own asteroid belt. Nestled between the orbits of Mars and Jupiter lies Ceres, a dwarf planet that for a long time was written off as a barren, rocky relic from the solar system's formation. That all changed when NASA's Dawn spacecraft arrived, revealing a world far more complex and intriguing than anyone had anticipated. Dawn's instruments didn't just map the surface, they detected the clear and unmistakable signature of complex organic molecules, the fundamental chemical building blocks essential for life as we know it. These aren't just simple carbon compounds. We're talking about the types of carbon-rich, complex materials that, under the right conditions, can lead to the formation of amino acids and other precursors to biology. The presence of these organics on Ceres is revolutionary because it challenges our very understanding of where these vital ingredients can form and survive. Ceres is not a warm, wet world like the early Earth. It's a small, cold body that has been around since the dawn of our solar system. The fact that such fragile molecules have persisted for billions of years suggests they might be embedded within Ceres's interior, potentially protected by a subsurface layer of briny water. This creates a powerful new narrative. If the ingredients for life can be generated and preserved on a small, icy world like Ceres, then they could be incredibly common throughout the cosmos, seeded across countless planetary systems. This discovery provides a tangible, alternate pathway for how life might have begun on our own planet. The prevailing theory of panspermia suggests that the basic building blocks of life, or even life itself, could have been delivered to Earth by asteroids and comets during the solar system's violent early days. Ceres, as a large protoplanet that never fully formed into a larger world, acts as a pristine time capsule from that era. Finding a rich reservoir of organics on such a body offers compelling evidence that the celestial objects bombarding the young Earth weren't just bringers of destruction. They could very well have been the couriers that delivered the essential raw materials for biology. Our very existence might be thanks to the cosmic freight shipped from the outer solar system. Beyond its implications for our origins, Ceres reshapes our search strategy for life elsewhere. We often focus our efforts on Earth like planets orbiting Sun like stars, but Ceres demonstrates that we should be looking at the small, icy moons and dwarf planets in our own backyard with renewed vigor. Worlds like Jupiter's moon Europa or Saturn's moon Enceladus have subsurface oceans, and if a relatively dry world like Ceres can host complex organics, then those watery moons could be veritable factories for prebiotic chemistry. The universe may be filled with such small, icy bodies, each one a potential crucible for the first steps toward life, proving that you don't need a twin of Earth to host the ingredients of biology. This expands the habitable real estate of the universe exponentially, suggesting that life could be starting in the dark, cold reaches of space, far from the warmth of any star. This next discovery doesn't involve something we can see or touch, but rather the very fabric of reality itself. For a century, gravitational waves existed only in the equations of Albert Einstein's general theory of relativity. He predicted that cataclysmic events in the cosmos, like the collision of two black holes, would create ripples in spacetime, much like a stone dropped in a pond. But detecting these ripples seemed nearly impossible. By the time they reached Earth, they would be vanishingly faint, distorting the fabric of the universe by a distance tinier than the nucleus of an atom. The scientific triumph of finally confirming their existence in 2015 didn't just prove Einstein right, it handed humanity an entirely new sense with which to perceive the universe. We are no longer just stargazers, we are now universe listeners. This new sense is already revolutionizing astronomy. For all of human history, we have studied the cosmos through light, from visible waves to radio and X-rays. But light can be blocked, distorted, or absorbed. Gravitational waves are different, they pass through everything. This allows us to observe phenomena that were previously invisible, like the moment two black holes spiral into each other and merge. We are now hearing the dark, silent dramas of the universe unfold. This grants us an unprecedented window into the most extreme environments, teaching us about the nature of gravity, the properties of dense matter in neutron stars, and the very birth of the universe itself. It's the difference between watching a silent movie and suddenly experiencing it in full surround sound with all its depth and vibration. The technological spin-offs from this discovery are poised to transform fields far beyond astronomy. To detect these minuscule waves, scientists had to build LIGO, the Laser Interferometer Gravitational Wave Observatory, arguably the most precise measuring instrument ever created. Its lasers measure changes in distance so small they are almost incomprehensible. The advanced optics, vibration damping systems, and quantum squeezing techniques developed for LIGO are already finding applications in medicine, geology, and communications. Imagine ultra-sensitive listening devices that can detect the faintest rumblings of an earthquake long before it strikes, or medical imaging technology so precise it can spot a single cancerous cell hidden deep within tissue. The quest to listen to the cosmos is driving a quiet revolution in precision engineering here on Earth. Perhaps one of the most profound future applications could be in providing us with an early warning system for existential threats. Certain cosmic events, like the merger of neutron stars, are thought to be the source of heavy elements like gold and platinum, and they also emit bursts of gamma radiation. If a gamma-ray burst were to happen too close to Earth and be pointed in our direction, it could strip away our ozone layer, triggering a mass extinction event. Gravitational waves travel at the speed of light and arrive instantaneously, but the potentially harmful radiation that might follow could be delayed. If our gravitational wave detectors pick up the signature of such a merger within our galactic neighborhood, they could provide us with a crucial few seconds, minutes, or even hours of warning. This would give us a chance to take protective measures for our satellites and power grids, potentially safeguarding our technological civilization. The ability to hear the ripples from a catastrophic event millions of light years away could one day be the very thing that ensures life on Earth continues undisturbed. Yet another of our solar system's icy moons holds a secret that could rewrite the rules of biology and provide a new lens through which to view our own world. Europa, one of Jupiter's largest moons, has long captivated scientists, but it wasn't until recent missions that we confirmed a staggering truth. Beneath its cracked and frozen exterior lies a vast global subsurface ocean containing more than twice the volume of all Earth's oceans combined. This isn't a shallow layer of slush. It's a deep, salty, liquid water world kept warm not by the distant sun, but by the immense gravitational forces of Jupiter itself, which flex and heat Europa's core through a process known as tidal heating. This revelation transforms Europa from a distant, frozen rock into one of the most promising places to search for life beyond Earth. The implications for understanding our own planet's oceans are profound. Earth's deep sea vents, where superheated, mineral-rich water erupts from the seafloor, are oases of life in the absolute darkness of the abyss. These ecosystems thrive on chemosynthesis, where microbes convert chemicals into energy without any need for sunlight. Europa's ocean is thought to possess similar hydrothermal vents on its seafloor, creating a potentially habitable environment entirely divorced from solar energy. By sending missions to probe Europa's ice shell and analyze the plumes of water vapor that occasionally erupt from its surface, we are essentially conducting a grand experiment in comparative oceanography. Studying how an ocean functions on a world with no atmosphere, no sunlight, and a completely different heat source gives us a new baseline to understand the fundamental principles of ocean chemistry, circulation, and the very origins of life. It helps us answer whether Earth's oceans are unique or if the recipe for a living ocean is a common feature throughout the cosmos. This exploration directly fuels the search for extraterrestrial life. The harsh conditions in Europa's ocean, extreme pressure, cold, and likely high salinity, are precisely the kinds of environments where we find extremophiles on Earth, organisms that push the boundaries of what we consider possible for life. If we were to discover that life has arisen independently in the dark, pressurized ocean of a moon orbiting Jupiter, it would suggest that life is not a delicate miracle but a robust and inevitable force wherever the right conditions persist. This knowledge would fundamentally shift our perspective, implying that the universe is likely filled with life, most of it microbial, waiting to be found in the subsurface oceans of icy worlds throughout our galaxy and beyond. Looking even further ahead, Europa's ocean represents more than just scientific curiosity. it could be a vital resource for humanity's future as a spacefaring species. Water is the oil of space exploration. Beyond its life-sustaining properties, it can be split into hydrogen and oxygen for rocket fuel and breathable air. A confirmed, accessible source of water on a body like Europa could serve as a crucial fueling depot for missions venturing deeper into the outer solar system, turning a distant moon into a cosmic waypoint. While the engineering challenges of accessing an ocean buried under miles of ice are monumental, the potential payoff is a permanent foothold in the outer solar system, enabling a new era of exploration and perhaps one day, even the establishment of research outposts where we can study this alien sea directly. But our exploration of Mars reveals more than just water. It offers a tantalizing chemical mystery that could point directly to biological activity. For years, orbiters and rovers like Curiosity have been detecting sporadic, unexplained spikes of methane gas in the Martian atmosphere. On Earth, the vast majority of methane is produced by living organisms, from microbes to livestock, making its presence on Mars one of the most compelling potential biosignatures we've ever encountered. The mystery isn't just its presence, but its behavior. These plumes appear and vanish seasonally and unpredictably, unlike the steady background level we might expect from a non-biological geological source. Pinpointing the origin of this methane is a scientific detective story with enormous stakes. If the source turns out to be geological, such as serpentinization, a process where water interacts with certain rocks to produce methane, it would still be a monumental find. It would indicate that Mars is far more geologically active than we ever believed, with complex chemical processes happening beneath its surface. This knowledge would reshape our understanding of the red planet's history and its potential to support subterranean environments where life could cling to existence. However, the possibility that the methane is being produced by methanogens, ancient and simple microbial life forms that metabolize hydrogen and carbon dioxide, is what truly captures the imagination. Finding even this simplest form of life on Mars would irrevocably answer the question of whether we are alone in the universe and prove that biology can arise on more than one world. Beyond the search for aliens, solving the methane mystery provides a crucial case study for our own planet's climate systems. Methane is a potent greenhouse gas, far more effective at trapping heat than carbon dioxide over the short term. By studying how methane is produced, stored, and released into the thin Martian atmosphere, we gain a simpler, more isolated model to understand the complex methane cycles here on Earth. This includes processes in permafrost, wetlands, and even the ocean floor. Mars acts as a natural laboratory, free from the overwhelming influence of a global biosphere, allowing us to test and refine our atmospheric models. This purer data can help us better predict the impact of methane releases on our own climate and inform strategies for mitigation. The technological drive to solve this puzzle is also accelerating innovation in sensor technology and robotic exploration. The instruments designed to detect trace amounts of gas on another world are marvels of precision engineering. These ultra-sensitive spectrometers and chromatographs are the direct ancestors of next-generation environmental monitoring equipment used on Earth. The same technology developed to sniff out methane plumes on Mars is now being adapted to pinpoint methane leaks from pipelines, landfills, and agricultural operations with incredible accuracy, helping us reduce a significant contributor to global warming. The quest to understand an alien atmosphere is directly equipping us with better tools to protect our own. Just when we thought we had our own solar system figured out, the cosmos sent us a visitor from a place we'd never been. In 2017, astronomers in Hawaii spotted something unprecedented. A small, fast-moving object hurtling through our solar system on a trajectory so extreme it could only have come from interstellar space. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. This wasn't a comet or asteroid from our own neighborhood. It was a genuine artifact from another star system, the first one ever observed. Its peculiar characteristics, an elongated, cigar-like shape, a peculiar spin, and an unexpected acceleration, ignited a firestorm of scientific debate and public fascination, including some far-out speculations about its origins. Studying such interstellar objects is like receiving a cosmic care package from a distant sun. Every comet and asteroid within our solar system is made of material that formed from the same primordial cloud of dust and gas, giving them a shared family history. Oumuamua had no such connection. Its composition and structure were forged around an entirely different star, offering us our first ever direct sample of how other planetary systems are built. By analyzing its path, its reflectivity, and the way it interacted with the sun, scientists could glean clues about its makeup and the environment it came from. This provides a critical data point for testing our theories of planet formation. It helps us answer a fundamental question: is our solar system's architecture common, or is it just one of many possible designs in the galaxy? Each new interstellar visitor we find, and we've found several since Oumuamua, adds another chapter to this growing catalogue of cosmic construction techniques. Beyond pure science, these objects hint at a future possibility that sounds like science fiction, mining resources from other star systems. While the engineering required to intercept and utilize an object traveling at such incredible speeds is far beyond our current capabilities, their existence proves that the building blocks of planets, metals, minerals, and even water ice are being exchanged between star systems. In a distant future, such visitors could be seen not just as scientific curiosities, but as potential reservoirs of exotic materials or elements that are rare in our own solar system. They represent the idea that the resources of the galaxy are not permanently locked away around their parent stars. The universe is constantly sharing its wealth, tossing these raw materials across the vast distances between suns. Perhaps the most immediate and practical application of studying interstellar objects lies in the field of planetary defense. Oumuamua's sudden appearance underscored a sobering reality: our solar system is permeable. If one natural object can wander in, so could another on a collision course with Earth. While the odds are incredibly low, the consequences would be unimaginably high. Tracking these fast-moving, often faint visitors is immense training for our global network of telescopes and early warning systems. It pushes our detection capabilities to their limits, forcing us to get better at spotting small, dark objects against the blackness of space with very little notice. This practice is invaluable for protecting our planet from more local threats like near-Earth asteroids. By honing our skills on these interstellar speedsters, we improve our ability to spot any potentially hazardous object sooner, giving us more time to assess the threat and, if necessary, mount a deflection mission. The messenger from afar, therefore, delivers a critical warning. To truly safeguard our world, we must vigilantly watch not just the space within our system, but the gates through which unexpected travelers can arrive. While the search for water and life captivates our imagination, some of the most profound discoveries in space involve something we cannot see at all, a ghost that permeates the cosmos and holds entire galaxies together. We've long known that the universe contains far more than meets the eye. The stars and galaxies we observe are merely the visible tip of a vast cosmic iceberg. The overwhelming majority of the universe's mass is made of dark matter, an invisible substance that does not emit, absorb, or reflect any light, yet its gravitational pull is the fundamental architect of our universe's large-scale structure. For decades, it was a concept we could only infer indirectly, but today, through breathtakingly precise mapping techniques, we are beginning to trace the shadowy skeleton of the cosmos. Scientists don't map dark matter by looking for it directly. Instead, they map its immense gravitational influence. One of the most powerful methods relies on a prediction from Einstein's theory of general relativity, that massive objects can warp the fabric of space-time, bending the path of light that travels past them. This phenomenon, called gravitational lensing, turns dark matter itself into a cosmic lens. When astronomers train their telescopes on distant galaxies, they can analyze how the light from those galaxies is subtly distorted as it passes through the invisible gravitational fields of vast dark matter halos. By meticulously measuring these tiny distortions across millions of galaxies, supercomputers can construct detailed three-dimensional maps of the dark matter web that spans the universe. It's a painstaking process of cosmic cartography, revealing the hidden architecture upon which all visible matter is hung. Understanding the true nature of this mysterious substance could unlock a scientific revolution far beyond astronomy. Our current model of physics, the Standard Model, is incredibly successful but is also known to be incomplete. It cannot explain what dark matter is. Identifying its particles would therefore necessitate a monumental rewrite of the laws of physics, potentially unifying the forces of nature and revealing new dimensions of reality. This isn't just abstract theorizing. Every time humanity has peeled back a new layer of physics, it has unleashed transformative technologies. The discovery of electromagnetism gave us the electric grid and global communication. Unlocking quantum mechanics brought forth the transistor, the laser, and the entire digital age. Solving dark matter could be the key to the next great technological leap, potentially granting us access to entirely new forms of energy or propulsion. Imagine for a moment if we could somehow harness dark matter. While this remains firmly in the realm of speculation, the potential is staggering. If dark matter particles can be isolated and understood, they might be manipulated to create gravitational fields, opening the door to technologies that today sound like pure science fiction. We could develop propulsion systems that don't rely on throwing mass out the back of a rocket, but instead manipulate space-time itself, making interstellar travel a tangible reality. Or we might discover new, stable forms of energy generation that operate on principles completely foreign to our current understanding of chemistry and nuclear physics. Furthermore, the techniques developed to map the invisible universe are already providing tangible benefits here on Earth. The algorithms used to sift through terabytes of telescope data to find the subtle signal of dark matter are now being adapted to solve complex problems in medicine, such as analyzing medical scans to detect the earliest signs of diseases like cancer with unprecedented precision. The incredibly sensitive detectors built to catch a hypothetical dark matter particle deep underground are pushing the boundaries of material science and low background radiation measurement, leading to better sensors for everything from national security to environmental monitoring. The quest to map the cosmos's greatest secret is once again gifting us with the tools to see our own world more clearly, proving that the pursuit of fundamental knowledge, even for its own sake, has a remarkable way of circling back to change life on Earth in the most unexpected and profound ways. Leaving behind the enigmatic dark matter that shapes the cosmos, we journey to a world that feels strangely familiar yet utterly alien. Saturn's largest moon, Titan, is a place of breathtaking paradox. It's the only moon in our solar system with a thick, hazy atmosphere, and the only other celestial body where we have found stable liquids resting on its surface. But these are not lakes of water, they are vast, placid pools of liquid methane and ethane, resting at a frigid -290 degrees Fahrenheit. The Cassini-Huygens mission gave us our first detailed look at this bizarre hydrologic cycle, where methane plays the role that water does on Earth, evaporating from the lakes, forming clouds, and falling back down as rain, carving river channels and shaping shorelines in the soft, icy bedrock. Studying this alien hydrocarbon cycle offers a profound new perspective on our own planet's environmental systems. On Earth, methane is a powerful but transient greenhouse gas, part of a complex carbon cycle driven by life and geology. On Titan, we see a world where methane is the dominant player in a much slower, more fundamental geological cycle, completely divorced from biology. By observing how methane behaves as a liquid, a vapor, and a solvent on a global scale without the complicating factor of a biosphere, we gain a purified model of fluid dynamics and atmospheric chemistry. This helps scientists refine climate models for Earth, offering clearer insights into how liquids and gases interact under different pressures and temperatures, and providing a deeper understanding of the basic physical principles that govern all planetary atmospheres, including our own. The presence of vast energy reserves on Titan also sparks a conversation about humanity's long-term future. These lakes are not merely scientific curiosities. They are colossal, naturally occurring reservoirs of hydrocarbons, dwarfing all known oil and gas deposits on Earth. While the immense distance and harsh conditions make extraction currently impractical, Titan stands as a testament to the abundance of raw materials available in our solar system. Understanding the geology and chemistry that created and maintains these lakes informs the field of astrosource utilization, the concept of using space-based resources to enable further exploration. The knowledge gained from Titan could one day be applied to extracting water from asteroids or processing Martian atmospheric gases, providing the fuel and breathable air for a self-sustaining human presence beyond Earth. Perhaps the most immediate technological payoff lies in the field of extreme environment robotics. To explore Titan's methane lakes, we cannot send a conventional rover. We need a new class of explorer. NASA is already developing concepts like the Dragonfly mission, a drone-like rotorcraft designed to fly through Titan's thick atmosphere, and even proposals for a submarine capable of plunging into the dark, cold depths of a methane sea. Engineering a vehicle to operate in such an environment pushes the boundaries of material science, autonomy, and power generation. The technologies developed for these missions, materials that remain flexible at cryogenic temperatures, autonomous navigation systems that can operate without human input for years, and power sources that can function far from the sun, have direct spin-offs on Earth. They could lead to more durable Arctic exploration equipment, advanced drones for disaster response in harsh conditions, and more robust autonomous systems for deep-sea research, turning the challenges of exploring an alien moon into solutions for navigating the most difficult environments on our own planet. Titan, with its eerily Earth-like landscapes built from completely different ingredients, challenges our definitions of habitability and resources, proving that the universe is far more inventive and full of potential than we could ever have imagined from our watery, blue world alone. While we often think of space as a distant realm, one of its most powerful forces regularly reaches out and touches our planet with potentially devastating consequences. Our Sun, the source of all life on Earth, also has a violent and unpredictable side. It regularly unleashes colossal eruptions of energy and magnetized plasma known as solar flares and coronal mass ejections. For most of human history, these events were little more than beautiful auroral displays. But in our technologically dependent age, a direct hit from a massive solar storm could be catastrophic, frying satellites, knocking out power grids, and crippling global communications for months or even years. This reality makes our 10th discovery, the dramatic advances in our ability to predict this space weather, one of the most immediately vital applications of space science for life on Earth. The challenge of forecasting these solar tantrums is immense. Unlike terrestrial weather, which happens in our atmosphere, space weather begins 93 million miles away on the surface of a roiling, nuclear fusion-powered star. Predicting it requires a fleet of sun-staring observatories, both in orbit and on the ground, working in concert. Missions like NAS, a Solar Dynamics Observatory, and the Parker Solar Probe provide a constant stream of high-resolution data, allowing scientists to monitor the complex magnetic fields on the Sun's surface. It is the tangling and sudden snapping of these magnetic field lines that triggers the eruptions. By applying sophisticated computer models and artificial intelligence to this data, scientists are now getting better than ever at identifying the precursors to a major event, sometimes providing crucial hours of warning before a billion-ton cloud of charged particles begins its journey toward us. The value of this early warning system cannot be overstated. A well-forecasted coronal mass ejection allows satellite operators to put their valuable assets into a safe mode, protecting sensitive electronics from being fried by the incoming radiation. Airlines can reroute polar flights to avoid exposing passengers and crews to heightened radiation levels. Most critically, power grid operators can take defensive measures. When a massive wave of charged particles strikes Earth's magnetic field, it induces powerful electrical currents in the ground itself. These geomagnetically induced currents can overload and destroy the massive transformers that form the backbone of our electrical grids. A warning gives utilities time to bring extra power generation online, to isolate vulnerable equipment, and to prepare for potential instability, potentially preventing a cascade of failures that could leave millions in the dark. The economic impact of averted disaster is staggering. A 2013 study by the Lloyd's of London insurance market estimated that a major solar storm hitting the eastern seaboard of the United States could leave 40 million people without power for periods ranging from 2 weeks to 2 years, with total economic costs reaching $2.6 trillion. The comparatively tiny investment in space weather monitoring and prediction is arguably one of the best forms of planetary insurance we have. The technology developed for these solar observatories also finds its way back to Earth. The advanced optics and image processing algorithms used to track sunspots are now used in manufacturing for quality control, and the radiation-hardened electronics developed for satellites are used in medical imaging and nuclear safety systems. Looking ahead, the goal is to move from hours of warning to days. This would require even deeper understanding and better modeling of the Sun's internal dynamics. Future missions aim to create a comprehensive, three-dimensional view of the Sun's magnetic field, allowing us to see the build-up of energy before it even reaches the surface. This isn't just about protecting what we have, it's about enabling our future, as we become more dependent on global navigation systems like GPS for everything from banking to transportation, and as we dream of establishing a permanent human presence on the Moon and Mars, where astronauts would be fully exposed to solar radiation-accurate space weather forecasting becomes non-negotiable. It transforms from a scientific curiosity into a fundamental pillar of our technological civilization, a silent guardian that allows us to harness the Sun's light while respectfully dodging its occasional fury. But what if the key to solving resource scarcity on Earth isn't buried in our own ground, but is instead floating in abundance just waiting to be collected? This brings us to an endeavor that sounds like pure science fiction but is rapidly approaching reality: asteroid mining. Our robotic prospectors have already identified a class of space rocks known as metallic or M-type asteroids, which are essentially the exposed, battered cores of ancient protoplanets. These cosmic nuggets are incredibly rich in precious metals like platinum, gold, cobalt, and nickel, as well as rare earth elements that are absolutely vital for our modern technology, from smartphones and electric vehicle batteries to advanced medical imaging devices and military hardware. The potential to alleviate Earth's resource strains is monumental. Many of these critical elements are notoriously difficult and environmentally destructive to mine on our planet. Their extraction often involves devastating open-pit mining, generates massive amounts of toxic waste, and is frequently concentrated in geopolitically unstable regions, leading to volatile supply chains and ethical concerns. Accessing a single, relatively small metallic asteroid could provide more of these metals than has been mined in all of human history, effectively ending scarcity for certain elements and dramatically reducing the environmental and human cost of their acquisition. This wouldn't just make our gadgets cheaper, it could underpin a new, sustainable industrial revolution on Earth, providing the raw materials needed for a global transition to green energy and advanced technologies without further degrading our planet. Beyond transforming our economy on Earth, asteroid mining is the essential key to unlocking a truly sustainable future for space exploration itself. The concept of living off the land, known as in situ resource utilization, changes everything. The most immediately valuable resource isn't metal, it's water. We've already discovered countless water-rich asteroids, often called C-type asteroids. This water is a treasure trove. It can obviously support human life, but more importantly, it can be split into liquid hydrogen and liquid oxygen, the most powerful chemical rocket fuel combination we use. Imagine a future where spacecraft are refueled at orbiting depots supplied by asteroid miners, turning the solar system into a network of cosmic gas stations. This would mean we no longer have to launch every ounce of fuel from the bottom of Earth's deep gravity well, a process that is astronomically expensive and limiting. Suddenly, missions to Mars and beyond become far more affordable and frequent. This capability would enable the construction of massive structures in space that are currently impossible. Instead of launching all the raw materials from Earth, we could fabricate components using metals extracted from asteroids. We could build enormous space stations, vast solar power satellites to beam clean energy to Earth, and generation ships for interstellar travel. The technological challenges are immense: developing robotic miners, refining techniques in microgravity, and creating automated processing plants, but the payoffs redefine what's possible for our species. The same robotics and automation advances required to mine an asteroid autonomously, millions of miles from Earth, are already leading to breakthroughs in terrestrial mining, making it safer and more efficient through increased use of remote-operated and autonomous machinery. Asteroid mining ultimately offers a profound philosophical choice for humanity. It presents a path where we can choose to preserve our own planet by treating it as a protected garden, while meeting our material needs through the careful and sustainable harvesting of limitless space resources. It shifts our identity from a single-planet species, constrained by our world's finite limits, to a spacefaring civilization with access to the near-infinite resources of the solar system. The asteroids are no longer just distant rocks to be studied. They are the stepping stones and building blocks for our future, holding the potential to bring unprecedented prosperity to Earth while funding our greatest adventures among the stars. Yet as we reach for the stars, we are reminded of a silent, invisible danger that makes the vacuum of space and the lack of gravity seem almost manageable by comparison. This is the ever-present threat of cosmic radiation, a relentless hail of high-energy atomic particles that originates from the Sun and from cataclysmic events far across the galaxy. Unlike Earth, which is cocooned by its magnetic field and atmosphere, space offers no such protection. For astronauts on the International Space Station or on a journey to Mars, this radiation constantly bombards their bodies, damaging cells and DNA, and significantly increasing their lifetime risk of cancer, cataracts, and neurological diseases. Understanding and mitigating this hazard is the single greatest challenge for long-duration human spaceflight, and the solutions we are developing are poised to create a safer environment not just in space, but in hospitals and power plants here at home. The science of protecting astronauts is pushing the boundaries of material science and biology in incredible ways. We've moved far beyond the idea of simply wrapping a spacecraft in thick metal, which can actually make the problem worse by causing incoming particles to splinter into a secondary shower of even more radiation. Instead, researchers are taking a multi-layered approach, drawing inspiration from nature itself. One of the most promising concepts involves using water. Since water is rich in hydrogen atoms, which are excellent at blocking radiation, engineers are designing spacecraft hulls with integrated water walls, literally using the astronaut's own water supply as a protective barrier. Other teams are looking at active shielding, recreating a miniature version of Earth's magnetic field around a spacecraft to gently deflect charged particles away. A concept that sounds like it's straight out of science fiction but is moving closer to reality. Perhaps the most revolutionary area of research involves biological countermeasures. Scientists are studying the incredible resistance of certain extremophiles, like the tardigrade, which can survive lethal doses of radiation by entering a state of suspended animation and employing unique DNA repair proteins. By understanding these natural mechanisms, we are developing advanced pharmaceuticals that could one day be administered to astronauts to boost their own cellular repair systems, effectively helping their bodies heal from the inside out. This isn't just about pills, it includes research into specialized diets rich in antioxidants and even wearable tech that can monitor an astronaut's radiation exposure in real time, allowing for personalized countermeasures. The spin-offs from this cosmic research are already making a dramatic impact in the fight against cancer on Earth. The same advanced particle detectors used to measure radiation exposure in space are now being adapted to create a new generation of proton therapy machines for treating tumors. This technology allows oncologists to pinpoint cancers with millimeter precision, delivering a lethal dose of radiation to the tumor while sparing the surrounding healthy tissue, drastically reducing the debilitating side effects of traditional radiation therapy. Furthermore, the new shielding materials, lightweight, hydrogen-rich composites developed for spacecraft, are being used to build more compact and effective shielding around medical imaging equipment and nuclear reactors, making these facilities safer for technicians and patients alike. They also allow for smaller, more mobile X-ray and MRI machines that can be deployed in field hospitals or remote clinics, bringing advanced diagnostic capabilities to the places that need them most. This research is also providing us with a profound new understanding of human health in extreme environments. The data we gather on how radiation affects the human body at a cellular level during long-duration spaceflight is an accelerated model of the aging process and the cumulative damage we all experience from low-level environmental radiation throughout our lives. The insights gained could lead to breakthroughs in anti-aging treatments, neuroprotective therapies for degenerative brain diseases, and a deeper fundamental knowledge of human biology. The quest to protect a handful of explorers on their journey to Mars is yielding discoveries that will protect and heal millions of people right here on Earth, proving once again that the greatest benefits of looking outward are often found by looking inward at our own health and longevity. But perhaps no single image has ever captured the public imagination and scientific ambition quite like our next discovery, the first direct visual evidence of a black hole. For generations, these cosmic enigmas existed purely in the realm of theory and mathematical equations, the ultimate prediction of Einstein's general relativity. They were described as regions of spacetime where gravity is so intense that not even light can escape, a concept so bizarre it defied visualization. All of that changed in April 2019, when the Event Horizon Telescope collaboration unveiled an image that made history, a fiery, donut-shaped ring of light encircling a perfect circle of utter darkness. This was the supermassive black hole at the heart of the Messier 87 galaxy, 55 million light-years away, and its capture was a monumental feat of human ingenuity. Creating this image was less like taking a photograph and more like a breathtaking act of global synchronization. The Event Horizon Telescope isn't a single instrument. It's a planet-scale array of 8 radio observatories spanning from the high deserts of Chile to the volcanoes of Hawaii and the frozen peaks of Antarctica. By synchronizing these telescopes using atomic clocks, scientists effectively created a virtual dish the size of Earth itself, the only instrument with enough resolving power to see the shadow of a black hole against the glowing plasma that surrounds it. The amount of data collected was so vast it couldn't be sent over the internet. It had to be physically shipped on hundreds of hard drives to central processing centers where supercomputers correlated the signals for over 2 years to reconstruct this single, iconic image. The scientific payoff was immediate and profound. That dark shadow at the center of the glowing ring is the black hole's event horizon, the point of no return, and its size and shape match Einstein's predictions with stunning accuracy. This provides the strongest experimental evidence yet for his theory of general relativity under the most extreme gravitational conditions imaginable. By studying the asymmetry and brightness of the ring, astronomers can now understand how matter behaves as it spirals inward at nearly the speed of light, heating up to billions of degrees and creating powerful magnetic fields and jets that shoot out across intergalactic space. This allows us to finally test our models of how these cosmic engines work, solving mysteries that have persisted for decades about how black holes influence the evolution of the galaxies that host them. The technological legacy of this achievement is already seeding innovations far beyond astronomy. The mind-boggling algorithms developed to stitch together a coherent picture from fragmented and noisy data across a planet-sized telescope are groundbreaking. These techniques are now being adapted to revolutionize medical imaging. The same algorithms that sharpen the blurry data of a black hole are being used to enhance MRI and CT scans, allowing doctors to see finer details with shorter scan times, leading to earlier and more accurate diagnoses of conditions like tumors and neurological diseases. Furthermore, the incredibly precise atomic clock synchronization required for the telescope array is advancing the field of timekeeping itself, which is the backbone of everything from global navigation satellite systems like GPS to the high-frequency trading networks that underpin the world's financial markets. Looking to the future, the lessons learned from imaging a black hole could one day pave the way for technologies that sound like they belong in a futuristic novel. A deeper understanding of gravity and space-time is the first step toward concepts like advanced propulsion. While still theoretical, researching how black holes warp the fabric of the universe brings us closer to understanding if manipulating gravity itself for travel could ever be possible. Moreover, studying the chaotic environment around a black hole, where matter is converted into immense amounts of energy with staggering efficiency, could inspire entirely new paradigms for energy generation here on Earth. The first image of a black hole did more than just confirm a century-old theory. It opened a new window into the most extreme physics in the universe, and the technologies born from that effort are quietly beginning to reshape our world, proving that even the most abstract quest for knowledge can yield profoundly practical rewards. Yet, if the search for life on Mars and the icy moons represents looking for a needle in a cosmic haystack, our next discovery suggests the needle might have been hiding in plain sight all along, hanging in the acidic clouds of our closest planetary neighbor. Venus has long been considered a cautionary tale of a runaway greenhouse effect, a hellish world with surface temperatures hot enough to melt lead and pressures that would crush a submarine. It was the last place anyone expected to find even a hint of life. That's why the astronomical community was sent into a frenzy when, in 2020, a team of researchers announced they had detected the spectral signature of phosphine gas high in the temperate cloud layers of Venus's atmosphere. On Earth, phosphine is a gas that is almost exclusively associated with life. It's produced by certain kinds of bacteria that thrive in oxygen-free environments like swamps and animal guts, or it is manufactured industrially. While there are some known non-biological ways to make it, such as in the extreme conditions within the mantle of a gas giant planet, none of those processes should be possible on a rocky world like Venus. Its presence there is a profound and tantalizing mystery. This discovery immediately ignited a fierce and healthy scientific debate, which is exactly how the process of discovery is supposed to work. Other research groups scrambled to analyze the data or search for the signal with different telescopes, with some confirming the initial finding and others questioning the methods of interpretation. The controversy itself is a powerful driver of scientific progress, pushing our observational techniques to their absolute limits. It forces us to build better instruments and to question our most fundamental assumptions. The central question is both simple and revolutionary. If this phosphine isn't being produced by some previously unknown abiotic chemistry unique to Venus, could it be a metabolic byproduct of microbial life floating high in the Venusian clouds? At an altitude of about 30 to 40 miles, the temperature and pressure are surprisingly Earth-like. While the clouds are composed of sulfuric acid droplets, a harsh environment to be sure, we know of extremophile microbes on Earth that are not only tolerant of acidic conditions but actually thrive in them. The implications for the search for life are utterly transformative. For decades, the guiding mantra has been "follow the water," leading us to focus on Mars and the icy moons. Venus forces us to broaden that perspective dramatically. It suggests that life, if it exists, could be far more ingenious and resilient than we ever imagined, capable of carving out a niche in the most unexpected and hostile environments. This expands the very definition of a habitable zone. A planet doesn't necessarily need a benign surface. Life could potentially exist in the atmospheric layers of countless worlds across the galaxy, from the gas giants in our own solar system to the hazy super-Earths orbiting distant stars. Venus challenges our Earth-centric biases and opens up entirely new categories of worlds to consider in our grand cosmic census. Verifying this discovery is the next great challenge, and it is already catalyzing a new wave of proposed space missions designed to answer this specific question. These aren't just orbiters. Concepts include balloons and aerial platforms that could float directly within the Venusian cloud decks, sampling the air, analyzing the droplets, and searching for direct evidence of organic molecules or even microbial cells themselves. The technology required to operate in that searing, corrosive environment is pushing the boundaries of material science, leading to the development of new alloys, sensors, and power systems that can withstand incredible abuse. These advancements will inevitably find uses back on Earth, from creating more durable environmental sensors for monitoring industrial pollution to developing new protective coatings for equipment used in extreme conditions. The quest to solve the mystery of Venusian phosphine, whether it ultimately reveals a new branch of biology or a fascinating new type of planetary chemistry, is already reshaping our approach to exploration and reminding us that the universe is always ready to surprise us. Now, let's shift our focus from the mysteries of other worlds to a tangible solution for our own, one that could literally power our future from the heavens above. For decades, the dream of harnessing the sun's energy directly in space has captivated scientists and engineers. The concept is as brilliant as it is simple. Place massive solar arrays in orbit where they can bask in uninterrupted 24/7 sunlight, free from clouds, night, or atmospheric filtering. These satellites would then convert that raw solar power into microwaves or lasers and beam it wirelessly down to receiving stations on Earth called rectennas, which would convert it back into electricity and feed it directly into the power grid. This isn't science fiction, it's a serious engineering pursuit that's gaining incredible momentum, and it promises nothing less than a revolution in how we power our civilization. The advantages over terrestrial solar power are staggering. A solar panel in geostationary orbit receives more than 10 times the amount of energy per unit area than one on the ground, and it does so constantly. Unlike Earth-based renewables, which are plagued by intermittency, the sun doesn't always shine and the wind doesn't always blow. Space-based solar power offers a truly baseload source of clean energy. It could provide a reliable, always-on stream of electricity to any point on the globe, day or night, in any weather. This solves the single biggest hurdle in the transition to renewables, the need for massive, expensive battery storage to overcome lulls in generation. A network of these power-beaming satellites could form a resilient global energy web, reducing reliance on fossil fuels and providing a stable power supply to remote communities, disaster zones, and developing nations without the need to build out vast and vulnerable terrestrial infrastructure. The technological hurdles that once seemed insurmountable are now being tackled with breathtaking innovation. The key challenge has always been the colossal cost of launching the necessary infrastructure. But with the advent of reusable rockets from companies like SpaceX, launch costs are plummeting. Furthermore, engineers are designing ultra-lightweight, modular solar panels and reflectors that can be folded up for launch and then unfurled autonomously in space like a giant flower blooming in the void. Robotics and in-space manufacturing techniques are advancing to the point where these massive structures could potentially be assembled by autonomous machines, using raw materials harvested from the moon or nearby asteroids, further reducing the need to launch everything from Earth. Perhaps the most publicly scrutinized aspect is the safety of beaming energy through the atmosphere. Research has consistently shown that a low-intensity microwave beam at the frequencies proposed would be perfectly safe. It would be no more dense than the sunlight already falling on us, and the beam would be precisely targeted and tightly controlled with multiple fail-safes. It would be designed to disperse harmlessly if it ever drifted off its target rectina, which itself would be a large, open mesh structure that could easily share the land with farming or other activities. The real breakthrough is in the efficiency of this power conversion process. Recent laboratory demonstrations have successfully beamed power over significant distances with minimal loss, proving the core physics is sound. The geopolitical and economic implications are as profound as the technological ones. Access to limitless, clean energy from space could fundamentally alter global power dynamics, moving nations away from conflicts over scarce fossil fuel resources and toward cooperation on a shared astronomical infrastructure project. It could provide the abundant, cheap energy needed to tackle some of humanity's greatest challenges, from large-scale desalination to solve water scarcity to powering direct air capture systems that remove carbon dioxide from the atmosphere. The pursuit of this technology is already driving advances in wireless power transmission, high-efficiency photovoltaics, and autonomous robotics innovations that are finding immediate applications in consumer electronics, electric vehicle charging, and disaster relief efforts here on the ground. Space-based solar power represents more than just a new power plant. It represents a paradigm shift, turning our entire planet into a recipient of energy from the ultimate source, the sun, and in doing so, offering a permanently sustainable future for everyone on Earth. While we often imagine space as the final, sterile frontier, a series of remarkable experiments have revealed a shocking truth. It is teeming with life, or at least life's incredible potential. For decades, scientists have been conducting a unique experiment, exposing hardy microorganisms to the absolute vacuum of space, the relentless bombardment of solar and cosmic radiation, and the wild temperature swings that would instantly kill any human. And the results have been nothing short of astonishing. Certain microbes, particularly tough bacteria like Deinococcus radiodurans and the bizarre eight-legged tardigrades, don't just die. They enter a state of suspended animation, curling into a dry, glass-like ball called a ton state, and simply wait. They have been revived after years of exposure, showing that life, even in its simplest forms, possesses a resilience that borders on the indestructible. This discovery forces a profound and immediate shift in how we explore the solar system under a concept known as planetary protection. If a tiny microbe from Earth can hitch a ride on a spacecraft and survive the journey to Mars, it could contaminate the very environments we are trying to study. A false positive for life on the red planet could be nothing more than a stowaway from Florida. This isn't just a scientific concern, it's an ethical one. We have a responsibility to preserve other worlds in their pristine states, to study them as they are, not as we might inadvertently change them. As a result, space agencies now implement incredibly stringent sterilization protocols for spacecraft, especially those destined for potentially habitable worlds like Mars or the icy moon. Every component is baked, bathed in harsh chemicals, and assembled in clean rooms that are far more sterile than any hospital operating theater. The knowledge that life can survive this journey means we must be ever more vigilant, treating our spacecraft not just as vehicles of discovery, but as potential arks that must not carry any unintended passenger. Beyond safeguarding other planets, this research is sparking a revolution in biotechnology right here on Earth. Scientists are intently studying the unique mechanisms these space-hardy microbes use to protect themselves. How does the tardigrade manufacture special proteins that form a protective glass shield around its cells? How does Deinococcus radiodurans possess such an incredibly efficient DNA repair toolkit that it can stitch its genome back together after it has been shattered by radiation? By unlocking these biological secrets, we are developing new technologies. This includes advanced stabilizing agents for vaccines and pharmaceuticals that wouldn't require refrigeration, a game changer for delivering medicines to remote parts of the world. It's leading to more robust industrial enzymes that can function in extreme conditions, and even new kinds of radiation-resistant materials inspired by biological blueprints. The extremophiles teaching us how to survive in space are also showing us how to build a better, more resilient future on our own planet. Ultimately, the most staggering implication is for our understanding of life's journey across the cosmos. The fact that microorganisms can survive in space for years lends powerful credibility to the theory of panspermia, the idea that life itself could be spread from planet to planet, and even star to star by hitchhiking on asteroids, comets, or even interstellar dust. A rock blasted off the surface of Mars by an asteroid impact could carry these resilient spores across the void, eventually landing on a young and welcoming world like Earth billions of years ago. This suggests that life may not have originated on our planet at all, but could have been a gift from the heavens, a seed planted in our primordial oceans. If that's true, then the story of life on Earth is not an isolated chapter but part of a grand galactic narrative. The building blocks of biology, and perhaps even life itself, might be a natural and widespread product of cosmic evolution, waiting for the right conditions to take root and flourish. The incredible durability of a simple microbe forces us to see the solar system not as a collection of separate worlds, but as a connected biological system where life might be constantly exchanged, making the universe feel far more alive and interconnected than we ever dreamed. But just as we contemplate the cosmic origins of life itself, we turn to a discovery that promises to secure the very information that defines our modern existence. In an era where digital espionage and cyberattacks threaten national security and personal privacy, scientists have looked to the heavens for a solution rooted in the fundamental laws of physics. Enter the world of quantum communication satellites, a technology that doesn't just improve upon current encryption methods, but renders them fundamentally obsolete by harnessing the bizarre and counterintuitive rules of the quantum world. At the heart of this revolution is a phenomenon called quantum entanglement, which Einstein himself famously described as spooky action at a distance. It's a process where two particles, like photons of light, become inextricably linked. No matter how far apart they are separated, whether it's across a lab or across the solar system, the state of one particle instantly influences the state of its partner. This isn't just a theoretical curiosity, it's the key to creating encryption keys that are impossible to intercept or copy. The moment a hacker tries to eavesdrop on a quantum key distribution, their act of measurement unavoidably disturbs the delicate quantum state of the particles. This disturbance is immediately detectable to the legitimate users, alerting them to the breach and causing the compromised key to be instantly discarded. It's not that the encryption is difficult to break, it's that the laws of physics themselves make undetected interception a literal impossibility. The challenge, however, has been distance. Sending these fragile quantum signals through optical fibers on the ground is like trying to whisper a secret through a miles-long pipe. The signal degrades and is lost after about 100 miles. This is where satellites provide the perfect solution. By beaming entangled photons down to separate ground stations on Earth from a satellite orbiting overhead, we can create a global quantum network. The satellite acts as a trusted relay, distributing unbreakable keys between any 2 points on the globe that can see it. China's Misha satellite has already spectacularly demonstrated this, establishing secure video links between Beijing and Vienna and performing quantum teleportation experiments over record-breaking distances. This isn't just a laboratory experiment, it's a working prototype for a future quantum internet. The implications for global cybersecurity are nothing short of revolutionary. Imagine a world where financial transactions, government communications, and critical infrastructure controls are protected by encryption that is permanently secure against any conceivable computational attack, even from future quantum computers that could easily crack today's best codes. This technology could safeguard the backbone of our digital society, from power grids and water treatment plants to military defense systems and voting platforms. It creates a foundation of trust in our digital interactions that is based not on complex mathematics, but on the unbreakable laws of the universe. The ripple effects of this technology extend far beyond secure messaging. The incredibly precise timing and synchronization required for these quantum satellite links are driving advances in other fields. The same techniques are being used to create networks of atomic clocks so precise that they could lead to a new global positioning system with centimeter-level accuracy, revolutionizing everything from autonomous vehicle navigation to geological monitoring for earthquake prediction. Furthermore, the effort to create a global quantum network is forcing unprecedented international collaboration in setting standards and protocols, fostering a new era of scientific diplomacy. As we extend this quantum web, we aren't just building a safer internet. We are laying the groundwork for a new technological era where the strange properties of quantum mechanics are harnessed not just for communication, but for sensing, computing, and exploring the universe in ways we are only beginning to imagine. Yet as we analyze the faint light of distant suns, a new field of science is emerging that brings the search for life into astonishingly sharp focus. We are moving beyond simply counting exoplanets to intimately dissecting their atmospheres, searching for the chemical fingerprints that could betray the presence of a living world. When an exoplanet transits or passes in front of its host star, a tiny fraction of the starlight filters through the planet's gaseous envelope. Powerful observatories like the James Webb Space Telescope act as interstellar chemists, separating this light into a spectrum, a unique barcode of absorption lines where specific molecules have stolen away specific colors. It is within these intricate patterns that we hunt for biosignatures, combinations of gases that are difficult to explain through geology alone. The simultaneous presence of both oxygen and methane, for instance, is a classic biomarker. On Earth, these gases react with each other and would quickly cancel out unless they are being constantly replenished by biological processes. This atmospheric analysis provides us with a powerful mirror to understand our own planet's past, present, and potential future. We are not just looking for twins of modern Earth, we are finding worlds frozen at different stages of planetary evolution. Some exoplanets show the thick, Venus-like signatures of a runaway greenhouse effect, with atmospheres dominated by carbon dioxide and suffocated by clouds of sulfuric acid. Others might resemble a younger, probiotic Earth, hazy with organic smog. By comparing these snapshots, we can piece together a grand narrative of how terrestrial planets live and die. This allows us to run a universal test on our climate models. If we observe a planet with twice the carbon dioxide of Earth and a surface temperature of 200 degrees Celsius, it confirms our understanding of the greenhouse effect under extreme conditions. This comparative planetology provides vital data that helps us refine predictions for our own world's climate trajectory, offering a sobering glimpse of potential futures we must strive to avoid. The ultimate goal, of course, is to find a world that not only resides in the habitable zone, but also displays that telltale cocktail of gases suggesting a living, breathing biosphere. Discovering such a world would fundamentally alter our understanding of our place in the universe, proving that the genesis of life is not a singular miracle but a natural cosmic process. However, this search also highlights the incredible fragility and rarity of Earth's precise environmental balance. We are finding that a stable, temperate climate over billions of years, a prerequisite for complex life, requires a delicate and complex interplay of factors: a robust magnetic field to shield the atmosphere from stellar winds, plate tectonics to recycle carbon and regulate temperatures, and even a large moon to stabilize the planetary tilt and prevent chaotic climate swings. The more exoplanets we study, the more we appreciate that Earth is not just a planet that has life. It is a planet meticulously fine-tuned for life, a precious and perhaps exceedingly rare jewel in the vast cosmic dark. But what if one of the most profound benefits of leaving Earth isn't just about what we find out there, but what we can create once we break free from gravity's constant pull? This brings us to a revolutionary frontier that is already yielding results: manufacturing in the pristine environment of microgravity. For centuries, industry on Earth has been a constant battle against gravity's pervasive influence. It causes convection currents in fluids, leads to sedimentation and separation in mixtures, and imposes severe limitations on the structures of delicate crystals and proteins. In the weightlessness of orbit, however, these constraints vanish, opening up a new world of possibilities for creating things that are simply impossible to make on our planet. The implications for medicine are nothing short of transformative. Consider the process of growing protein crystals for drug development. On Earth, these crystals are often misshapen and imperfect, crowded and deformed by gravity's pull as they form. This makes it incredibly difficult for scientists to determine their precise three-dimensional structure, which is the key to designing drugs that can target diseases with pinpoint accuracy. In microgravity, these crystals grow larger, more perfectly ordered, and with far fewer defects. This allows researchers to create exquisitely detailed molecular maps, dramatically accelerating the development of new, more effective pharmaceuticals for conditions like cancer, Parkinson's disease, and muscular dystrophy. We are essentially using the International Space Station as the ultimate laboratory for crystallography, uncovering the hidden blueprints of life to design better treatments for millions. Beyond pharmaceuticals, microgravity is a game-changer for material science. Imagine creating a new class of optical fiber, one so pure and transparent that it could transmit data over vastly longer distances with virtually no signal loss. On Earth, impurities and gravity-induced imperfections make this impossible. In space, companies are already manufacturing Z-bland fiber, a fluoride-based glass that is far superior to the silica-based fibers used today. The potential here is to supercharge the global internet infrastructure, creating a backbone for communications that is exponentially faster and more efficient. Similarly, researchers are experimenting with creating exotic metal alloys. On Earth, metals of different densities separate when you try to mix them in a liquid state like oil and water. In microgravity, they can be combined uniformly, creating revolutionary new materials that are lighter, stronger, and more heat-resistant, perfect for everything from more efficient jet engines to the next generation of spacecraft. Perhaps one of the most promising and personal applications is in the field of regenerative medicine, the ability to bioprint human tissues and organs. On Earth, attempting to print complex, three-dimensional structures like a liver or a kidney with living cells is a monumental challenge. The soft, biological inks collapse under their own weight, requiring elaborate scaffolding that can damage the cells. In microgravity, these delicate structures can be printed and maintain their shape layer by layer without any deformation. Researchers are already successfully bioprinting cardiac and vascular tissues aboard the space station, taking critical steps toward the ultimate goal of creating viable organs for transplant. This technology could one day end the agonizing wait for organ donors, offering personalized, printed organs grown from a patient's own cells, virtually eliminating the risk of rejection. The quiet, weightless environment of space is becoming a workshop for medical miracles, turning science fiction into a tangible future for healing. These microscopic grains, often smaller than a single bacterium, are the leftover building materials from the formation of stars and planets, and they carry within them the untold history of our galaxy's evolution. Unlike the large interstellar objects that occasionally pass through, this dust is a constant rain of information, a fine mist of cosmic sediment that settles throughout the solar system. For decades, scientists have been collecting these particles using high-altitude aircraft equipped with special collectors coated in a substance called aerogel, an incredibly light and porous material that gently slows and captures the dust without vaporizing it. It's like trying to catch a speeding bullet with a pillow, preserving its pristine state for laboratory analysis back on Earth. What these tiny messengers reveal is nothing short of a cosmic origin story written in mineral and ice. Each grain is a time capsule preserving the conditions of the specific stellar environment where it formed. Some particles are ancient, older than our own solar system, forged in the violent deaths of ancient stars and then blasted across the galaxy by stellar winds. By analyzing their isotopic ratios, the unique fingerprints of different forms of elements, scientists can trace a grain's lineage back to a specific type of star, like a red giant or a supernova. This allows us to literally hold a piece of another star in our hands and understand the nuclear furnaces that manufacture and spread the heavy elements essential for planets and life. We are conducting galactic archaeology, one microscopic speck at a time. This research directly illuminates our own beginnings. The prevailing theory of our solar system's formation suggests that a collapsing cloud of such interstellar gas and dust gave birth to our Sun and the protoplanetary disk that eventually coalesced into the planets. By studying the composition and structure of these contemporary interstellar particles, we are getting an unprecedented look at the very ingredients that went into making Earth. We are finding that these grains are rich in complex organic compounds, including carbon, the fundamental element of life. This supports the idea that the raw materials for biology were not invented here on Earth, but were delivered ready-made, sprinkled onto our young planet by comets and asteroids that were themselves made from this same cosmic dust. Our own planet and everything on it is quite literally made of stardust, and now we have the proof. The technological innovations driven by this delicate work are already finding critical applications. The challenge of capturing particles moving at hypervelocity has led to the development of advanced, ultra-lightweight materials like aerogel, which is now used in everything from super insulation for buildings to insulation for pipelines in extreme environments. The incredibly sensitive mass spectrometers and electron microscopes developed to analyze a single speck of dust without contaminating it are the precursors to next-generation medical and environmental sensors. These tools can detect trace levels of pollutants in the air or biomarkers for disease in a blood sample with unparalleled precision, all because scientists needed to measure the composition of a particle 1,000,000 times smaller than a grain of sand. Understanding the distribution and composition of cosmic dust also plays a surprising role in our exploration efforts. For missions traveling through the solar system, dust is a potential hazard, as high-speed impacts can damage sensitive instruments and spacecraft surfaces. By mapping the density and size of dust particles in different regions, we can better plan safe trajectories for future crewed missions to Mars and beyond. Furthermore, this knowledge helps us interpret data from our most powerful telescopes. Dust clouds can obscure our view of distant stars and galaxies, but by knowing exactly how dust scatters and absorbs light, we can subtract its effect from our observations, cleaning up the images and revealing the universe with sharper clarity than ever before. The study of the smallest things in the cosmos is therefore essential for seeing the biggest pictures, providing the crucial context needed to understand everything from the birth of a planet to the death of a star. Consider for a moment the wedding ring on a finger or the platinum in a catalytic converter. We often see these precious metals as symbols of earthly value and human achievement, but their true origin story is far more spectacular, written in the most violent events the universe has to offer. For decades, the cosmic forges that created the heaviest elements in nature remained one of astronomy's great mysteries. We understood that stars create lighter elements like carbon and oxygen in their cores, and that the immense pressures of supernova explosions can forge even heavier ones. But the creation of elements like gold, platinum, and uranium, a process that requires a frantic flood of neutrons to be jammed into atomic nuclei, required something even more extreme. The answer was finally confirmed in 2017, when astronomers witnessed the collision of two neutron stars for the very first time. A neutron star is the unimaginably dense corpse of a massive star that went supernova. Picture the mass of our entire sun crushed into a sphere the size of a city. A single teaspoon of its material would weigh billions of tons. When two of these incredible objects, locked in a gravitational dance, finally spiral together and collide, the energy released is beyond comprehension. The event observed in 2017, dubbed GW1 70817, sent ripples through the fabric of space-time gravitational waves that were detected here on Earth. Just moments later, telescopes around the globe and in space swiveled to look at the same patch of sky, capturing the brilliant flash of light and radiation from the aftermath. This multi-messenger astronomy, combining gravitational waves with electromagnetic observations, gave us a front-row seat to the cosmic drama. In the fiery crucible of that collision, conditions became so intense that handfuls of neutrons were ripped from the neutron stars and flung into the expanding cloud of debris. In this hot, dense, neutron-rich environment, a process known as rapid neutron capture, or the R process, went into overdrive. Atomic nuclei were bombarded with a blizzard of neutrons far faster than they could naturally decay, building up heavier and heavier elements in a matter of seconds. The observations showed clear spectroscopic signatures of newly forged elements like gold, platinum, and other precious metals being created in staggering quantities. Simulations suggest a single neutron star merger can produce hundreds of times the Earth's mass in gold alone, scattering these newly minted elements across the galaxy, where they eventually become incorporated into new stars and planets. This discovery fundamentally rewrites our own history. Every ounce of gold jewelry, every platinum medal, every trace of uranium in the Earth's crust was once forged in the cataclysmic collision of two dead stars that occurred billions of years ago, long before our solar system even existed. We are literally walking stardust, but for the heaviest elements, we are the product of something even more rare and violent. We are the ashes of neutron star mergers. This knowledge connects us to the cosmos in the most intimate way possible. The most prized possessions in human culture are souvenirs from the most destructive events in the universe. Beyond the poetry, this revelation has profound practical implications for science. By studying the light from these events, known as kilonovae, we can now quantify the production rates of heavy elements throughout cosmic history. This allows us to create a more accurate inventory of the universe's composition and understand the chemical evolution of galaxies, including our own Milky Way. The intense gamma-ray bursts that often accompany these collisions are also thought to be the universe's primary natural particle accelerators, creating conditions that we could never replicate on Earth. Understanding them helps us test the fundamental laws of physics under the most extreme energies imaginable. The observation of a single neutron star collision did more than just solve a long-standing mystery. It opened a new window into the violent, creative, and beautiful processes that continuously enrich the cosmos with the very materials that make our world and life itself possible. While we often gaze outward to unravel the mysteries of distant stars, some of the most astonishing discoveries are found by turning our orbital eyes back toward our own planet, revealing secrets hidden in plain sight for centuries. This is the emerging field of space archaeology, where satellites originally designed to study other worlds are now revolutionizing our understanding of our own ancient past. By peering down from hundreds of miles above the Earth, these sophisticated instruments are uncovering lost cities, buried roads, and forgotten monuments, completely transforming the practice of archaeology and offering an unprecedented tool for cultural preservation. The technology behind this revolution is as diverse as it is powerful. Modern satellites don't just take ordinary photographs, they capture data across a wide spectrum of light, including infrared and near-infrared wavelengths that are invisible to the human eye. This allows them to see subtle variations in soil density, moisture content, and vegetation health that often betray the presence of human-made structures hidden just beneath the surface. For instance, the stone foundations of an ancient wall will retain less moisture than the surrounding soil, causing the plants above them to grow slightly stunted and less healthy. From the ground, this is utterly imperceptible, but from space, these crop marks form clear, geometric patterns that outline the ghostly footprints of long-vanished buildings. Other satellites use radar to penetrate dry sand in desert regions, revealing entire road networks and settlements that were swallowed by dunes 1,000 years ago, perfectly preserved in the arid environment. This orbital perspective is shattering the traditional limits of ground-based archaeology. A team on foot can only survey a few square miles in a season, and they must already know roughly where to look. A satellite, on the other hand, can scan entire countries in a matter of days, systematically examining landscapes for the faintest traces of human activity. This has led to an explosion of discoveries, from a massive, previously unknown structure near the ancient city of Petra in Jordan, to thousands of lost medieval settlements across Europe, and even prehistoric mounds in the Americas that had been plowed flat by centuries of farming. We are effectively creating a new, global map of human history, adding chapters to our story that we never knew were missing. It allows archaeologists to ask bigger questions about trade routes, the rise and fall of civilizations, and how ancient societies interacted with their environment on a continental scale. Perhaps the most urgent application of this technology is in the race against time to protect our shared cultural heritage. Across conflict zones and regions rapidly developing with urban expansion and agriculture, countless archaeological sites are under immediate threat of being looted or destroyed before they are ever documented. Space archaeology provides a non-invasive way to monitor these vulnerable areas. Satellites can detect the telltale signs of illegal digging at known sites, allowing authorities to intervene. They can create detailed maps and 3D models of ancient structures, providing a permanent digital record in case the physical site is damaged by war, natural disasters, or climate change. This isn't just about studying the past, it's about actively preserving it for future generations, using the most advanced tools of the space age to safeguard the fragile remnants of our earliest achievements. The implications extend far beyond pure historical interest, offering profound lessons for our future. By studying how past civilizations managed their resources, responded to climate shifts like droughts, and ultimately succeeded or failed, we gain invaluable insights into the long-term challenges facing our own global society. The patterns of ancient water management in now arid regions can inform modern strategies for dealing with water scarcity. Understanding why some cities were abandoned can help us build more resilient communities today. The view from space provides the broad, interconnected context that ground-level analysis often misses. revealing how human societies have always been part of a complex and changing planetary system. This unique partnership between orbital technology and earthly exploration ensures that the silent testimonies of lost worlds continue to speak to us, guiding our path forward even as they illuminate the depth of our history. And just as we learn to read the stories written in ancient soil from space, we must also learn to read the invisible messages being sent to us from across the galaxy, messages that may hold a key to one of the most pressing questions of our time. High above the protective blanket of our atmosphere, our planet is constantly bombarded by cosmic rays, high-energy particles, primarily protons, that are accelerated across incomprehensible distances by the shockwaves of supernova explosions and the intense magnetic fields of distant black holes. For decades, these subatomic travelers were of interest mainly to physicists studying the universe's most extreme accelerators. But a fascinating and controversial line of research suggests these microscopic messengers from the depths of space might be actively shaping our weather and climate in a surprisingly direct way by influencing the very formation of clouds in our sky. The proposed mechanism is as elegant as it is complex. When these high-energy cosmic rays pierce our atmosphere, they collide with molecules of air, shattering them and creating a shower of secondary particles. This cascade of energy can ionize the air, knocking electrons off atoms and creating charged molecules. In the humid lower atmosphere, these ions can act as seeds around which water vapor begins to condense, forming the tiny droplets that eventually grow into clouds. It's a concept that links the colossal explosion of a star 1,000 light-years away to the formation of a rain cloud over a field here on Earth. The hypothesis suggests that when the sun is more active, its stronger magnetic field and solar wind act as a shield, deflecting more cosmic rays away from our planet. With fewer cosmic rays reaching our atmosphere, there would be fewer ions to seed clouds, potentially leading to less cloud cover. Since clouds reflect sunlight back into space, less cloud cover could mean a warmer planet. Conversely, during periods of low solar activity, more cosmic rays get through, potentially seeding more clouds and having a slight cooling effect. This idea forces us to reconsider the drivers of Earth's complex climate system. For years, the dominant models have focused on greenhouse gases, solar irradiance, and aerosol pollution as the primary levers controlling global temperature. The cosmic ray connection, often called the solar climate link, introduces another potential player, a natural modulator that could account for some of the historical warming and cooling trends that don't perfectly align with other factors. It doesn't Chinese letter our understanding of climate change. Rather, it could add a layer of nuance, helping to explain certain natural variations and improve the accuracy of our long-term predictions. By incorporating this cosmic influence into our climate models, we might finally be able to untangle the intricate dance between human-caused warming and the natural rhythms of our star and galaxy. The implications for weather forecasting are equally profound. If this connection holds, monitoring the flux of cosmic rays and solar activity could provide meteorologists with a new tool for seasonal forecasting. Understanding whether we are entering a period of higher or lower potential cloud seeding from space could improve predictions about precipitation patterns, drought risk, and even the intensity of monsoon seasons. This isn't about predicting if it will rain next Tuesday, but about understanding larger climatic shifts months or years in advance. The technology used to detect these faint cosmic signals is itself pushing the boundaries of sensor design, leading to more sensitive atmospheric monitoring stations that can track minute changes in our environment. Of course, this theory remains a subject of vigorous debate within the scientific community. Reproducing the effect in laboratory experiments has proven challenging, and quantifying its global impact amidst the noise of other climate forces is incredibly difficult. But this healthy scientific controversy is precisely what drives progress. It compels researchers to design ever more clever experiments, to launch satellites specifically designed to study aerosol and cloud formation, and to dive deeper into the paleoclimate record to look for correlations between cosmic ray flux and ancient temperature data preserved in ice cores and sediment layers. Whether the theory is ultimately fully validated, refined, or replaced, the pursuit of this cosmic connection is already gifting us with a richer, more sophisticated understanding of the delicate and dynamic system that makes our world habitable. It serves as a powerful reminder that we are not isolated on our planet. We are part of a connected cosmic ecosystem where the distant fury of dead stars might quietly influence the gentle patter of rain on our rooftops. Imagine the challenge of planning a multi-year mission to Mars and realizing you cannot possibly pack enough food for the entire journey. This isn't a hypothetical puzzle. It's the driving force behind one of the most practical and transformative fields of space research. For decades, a central goal of long-duration spaceflight has been achieving self-sufficiency, and that means learning how to grow food in the utterly alien environment of space. The experiments conducted aboard the International Space Station and in simulated habitats on Earth are far more than just gardening hobbies for astronauts. They are rigorous scientific trials that are yielding breakthroughs with the potential to revolutionize how we feed our own world, especially as we face the mounting pressures of a changing climate and growing population. The obstacles to farming in space are immense, and overcoming each one has forced a level of innovation that simply isn't required on Earth. Without gravity, water doesn't drain. It forms floating blobs that can drown plant roots or float away. There's no natural sunlight on a space station, so every photon must be artificially provided by specialized LED arrays, tuned to specific wavelengths that optimize plant growth. Perhaps most critically, there's no fertile soil, no buzzing bees to pollinate flowers, and no gentle rain. Every single variable nutrients, water, atmosphere, light must be meticulously measured and controlled within a closed-loop system. This has led to the development of advanced hydroponic and aeroponic technologies, where plant roots are suspended in a nutrient-rich mist or solution, receiving exactly what they need without any soil at all. These systems are incredibly efficient, using up to 90% less water than traditional agriculture because every drop is recaptured and recycled, with nothing lost to evaporation or runoff. The knowledge gained from these extraterrestrial gardens is already being transplanted to the most challenging environments right here on Earth. Consider arid regions where drought and poor soil have made conventional farming impossible. The water-conserving methods of space-based agriculture offer a blueprint for growing crops in deserts using minimal resources. Companies are now using these aeroponic systems to grow leafy greens and vegetables inside repurposed shipping containers in urban food deserts, on the rooftops of skyscrapers, and in communities where fresh produce is otherwise scarce or unaffordable. This technology decouples food production from the traditional constraints of geography and seasonality, allowing us to grow food vertically, locally, and year-round, drastically reducing the need for long-distance transportation and its associated carbon footprint. Furthermore, the relentless focus on maximizing yield in a tiny, controlled space is leading to the development of incredibly resilient crop varieties. Space scientists are not just engineers, they are botanists selectively breeding and genetically screening plants to thrive in stressful, confined conditions. They are identifying genes that allow certain plants to resist disease, tolerate higher levels of carbon dioxide, or prosper under artificial light. These supercharged cultivars are perfectly suited for the future of farming on a climate-volatile Earth, where heat waves, unexpected frosts, and new plant diseases are becoming more common. The goal is to create a portfolio of robust food sources that can ensure a reliable harvest even when traditional crops might fail. Perhaps the most profound lesson from space-based agriculture is the philosophical shift it represents, a move away from seeing farming as a battle to dominate nature and toward a model of precise, sustainable stewardship. On a space station, there is no waste. Every output from one process becomes an input for another. Astronauts' breath provides the carbon dioxide that plants need for photosynthesis. The plants, in turn, release oxygen and purify the air. Even organic waste can be composted and returned to the system as nutrient. This model of a circular, regenerative life support system is the ultimate expression of sustainability, and it provides a powerful template for rethinking our entire approach to resource management on Earth. As we learn to create self-sustaining ecosystems in the void of space, we are essentially learning how to better care for our own fragile planetary ecosystem, transforming the way we produce food from a resource-intensive burden into a closed-loop, life-giving process. And just as we expand our search for life to the atmospheres of distant worlds, we must also consider a possibility that could dwarf the number of habitable planets entirely. For years, our hunt for life beyond Earth has focused on finding another pale blue dot, a rocky planet orbiting within its star's Goldilocks zone. But what if the most common abodes for life aren't planets at all? Enter the thrilling frontier of exomoon hunting, the search for natural satellites orbiting planets in other solar systems. Our own solar system provides a powerful hint. While we have only one world known to be brimming with life, we have multiple moons, like Europa, Enceladus, and Titan, that are considered top candidates for hosting life, or at the very least, the conditions for it. If this pattern holds true across the galaxy, then moons could outnumber planets as potential habitats by orders of magnitude, exploding the real estate available for biology and forcing us to completely rethink where we should point our telescopes. The challenge of finding these distant moons is a testament to human ingenuity. Detecting an exoplanet is difficult enough. Spotting a moon orbiting one is like trying to see a firefly circling a distant lighthouse while both are shrouded in fog. Astronomers use two primary methods, both relying on exquisitely precise measurements. The first looks at the timing of a planet's transit. As a moon and its parent planet orbit their common center of gravity, the moon's gravity causes the planet to wobble slightly. This tiny wobble translates into minuscule variations in the precise timing of when the planet begins and ends its transit across the face of its star. The second method looks for a dip within a dip. As a moon transits, it too blocks a tiny fraction of the star's light, creating a second, even smaller dimming event just before, after, or even on top of the main planetary transit. Isolating this signal from the background noise of starlight requires data from incredibly powerful observatories like the James Webb Space Telescope, pushing the limits of what is observationally possible. The potential for habitability on these moons is a captivating thought experiment. Imagine a moon similar in size to Mars orbiting a gas giant planet. The planet itself would be far outside the star's traditional habitable zone, a frozen world. But if the moon has a rocky, active interior, heated by the relentless gravitational tug of war with its massive parent planet, it could maintain a vast, liquid water ocean beneath a protective icy shell, just like Europa. This tidal heating could provide a stable, billion-year-long energy source completely independent of the star's light. Furthermore, a thick atmosphere could be trapped by the moon's own gravity, or even siphoned from the gas giant's immense gaseous envelope. Such a world would have two sources of energy: faint warmth from its distant sun and intense geological heat from within, creating a potentially stable and complex environment perfect for fostering life. This expansive view of habitability doesn't just increase the number of potential homes for life, it completely changes the rules of the game. A star's habitable zone becomes less of a strict gateway and more of a general guideline. We can now consider frozen moons orbiting rogue planets that have been ejected from their solar systems and now drift alone in the dark interstellar void. Kept warm solely by tidal forces and insulated by a thick layer of ice, these lonely worlds could harbor subsurface oceans, making them potential oases of life in the cold emptiness between stars. The discovery of even one such habitable exomoon would force a seismic shift in our understanding of life's tenacity, suggesting that life could exist in a far wider range of environments than we ever thought possible, thriving in perpetual darkness under the gentle glow of a giant planet's reflected light. This pushes the boundaries of our imagination and redefines the very meaning of the word habitable in our cosmic vocabulary. While we look to the heavens for answers, a crisis of our own making is quietly unfolding right above our heads, one that threatens to sever our connection to the modern world. Imagine a realm cluttered with the ghostly remains of our ambition, a swirling cloud of defunct satellites, discarded rocket parts, and millions of shards of debris, all racing around Earth at speeds exceeding 17,000 miles per hour. This is the growing problem of space junk, and it poses a silent, escalating threat to the very infrastructure that makes our 21st century lives possible. Every GPS signal that guides your drive, every weather forecast that warns of a coming storm, every international phone call and financial transaction that relies on satellite links, all of it is vulnerable to a single, catastrophic collision in the unforgiving environment of low Earth orbit. The danger isn't just theoretical, it's a cascading phenomenon known as the Kessler syndrome. One collision creates thousands of new fragments, each capable of causing another collision, potentially triggering an unstoppable chain reaction that could render entire orbital regions unusable for generations. This isn't a distant future problem. The International Space Station regularly performs maneuvers to dodge trackable debris, and satellites already have to be designed with shields to withstand impacts from the countless tiny, untrackable pieces. The solution requires a two-pronged approach. First, drastically improving our ability to see and track this ever-growing population of debris, and second, developing the first-ever technologies to actively remove it. The field of space surveillance is undergoing a revolution to address the first challenge. Instead of relying solely on a handful of ground-based radars and telescopes, new companies are deploying vast constellations of advanced sensors and leveraging artificial intelligence to create a real-time, high-fidelity map of orbit. They're using everything from powerful new phased array radars that can track smaller objects to optical telescopes that can monitor objects in higher orbits. This isn't just about cataloging debris. It's about predicting its path with incredible accuracy, providing satellite operators with the actionable data they need to maneuver their valuable assets out of harm's way, turning a chaotic orbital environment into a managed traffic system. But tracking alone is not enough. We must also become cosmic custodians. The most exciting area of development is in active debris removal, a field that sounds like science fiction but is rapidly becoming science fact. Engineers are testing a breathtaking array of concepts to capture and deorbit defunct objects. Some proposals involve spacecraft equipped with robotic arms or nets to literally grab hold of old rocket bodies and gently guide them down to burn up in the atmosphere. Other, more elegant solutions include using magnetic tugs that can interact with the magnetic fields of certain satellites without ever making physical contact, or even deploying giant foam-filled projectiles that would expand around a piece of debris, increasing its surface area and drag to accelerate its natural orbital decay. The technology being pioneered for this cleanup mission has profound implications for security and sustainability on Earth. The advanced sensors developed for tracking space debris are directly applicable to monitoring our planet's surface, leading to better systems for maritime domain awareness, illegal fishing detection, and border security. The robotics and autonomous rendezvous software required for a spacecraft to gently capture a tumbling, non-cooperative object in orbit are the same technologies needed for in-space satellite repair and refueling, which would extend the lives of multi-million-dollar assets and reduce future waste. Perhaps most importantly, the very act of designing a mission to remove debris forces a new paradigm of responsibility. pushing for international agreements and designs that ensure future satellites are either equipped with their own deorbiting systems or are built to be captured and removed at the end of their lives. Successfully cleaning our orbital backyard would secure the vital services we depend on every day, from global communications and precise navigation to climate monitoring and disaster management. It would ensure that the pathways to space remain open for future generations of explorers, scientists, and entrepreneurs. This endeavor represents a critical step in our maturation as a spacefaring species, shifting from pioneers who explore and exploit to stewards who protect and preserve, ensuring that the greatest frontier remains accessible not just for us but for all who follow. But how do we even begin to map such an incomprehensibly vast cosmos? How do we measure the mind-bending distances to stars and galaxies to understand where they are, how they move, and where they're ultimately going? This brings us to one of the most fundamental and challenging pursuits in all of astronomy, the science of cosmic distance measurement. For centuries, this was astronomy's grandest puzzle, a problem of scales that seemed almost unsolvable. We couldn't simply stretch a tape measure to the moon, let alone to a star in a distant galaxy. Unlocking the universe's secrets first required that we learn how to measure it, and the ingenious solutions we've developed to chart the void are now quietly revolutionizing technology right here on the ground. The entire endeavor is built like a cosmic ladder, where each new rung relies on the certainty of the one below it. The first rung, parallax, is a method so intuitive you can demonstrate it by holding a finger in front of your face and closing one eye at a time. As the Earth orbits the Sun, our position changes, allowing us to observe nearby stars from slightly different angles against the backdrop of much more distant stars. By measuring this tiny shift, we can use basic trigonometry to calculate a star's distance with stunning accuracy. For most of history, this was only possible for a handful of the very closest stars, but space-based observatories like Gaia have transformed this field. By measuring the parallax of over 1 billion stars with micro-arcsecond precision, the equivalent of discerning the diameter of a human hair from 1,000 miles away, Gaia has constructed the most detailed 3D map of our galaxy ever made, providing the solid foundation upon which all further distance measurements are built. As we peer deeper into the cosmos, we need brighter signposts. This is where the true cosmic mile markers come into play: standard candles. These are celestial objects whose intrinsic brightness or luminosity we believe we know. The most famous of these are Cepheid variable stars, which pulse at a rate that is directly tied to their true brightness. By measuring how bright they appear from Earth and comparing it to their known intrinsic brightness, astronomers can calculate their distance with remarkable reliability. It was by using these stars that Edwin Hubble made his landmark discovery that the universe is expanding. An even more powerful standard candle emerged with Type 1a supernova. These are the thermonuclear explosions of white dwarf stars that have reached a very specific mass limit, causing them all to explode with nearly identical peak brightness. They are so brilliant they can outshine an entire galaxy, allowing us to see them and measure their distances across billions of light years. It was by meticulously measuring these supernovae that astronomers made the shocking discovery that the expansion of the universe is not slowing down, as everyone expected, but is actually accelerating, a finding that revealed the existence of the mysterious dark energy. This relentless pursuit of precision in measuring the heavens has had a profound and unexpected impact on a technology most of us use every single day: the Global Positioning System. GPS is, at its heart, a spectacularly precise timekeeping and distance measurement network. Each satellite in the constellation contains an atomic clock and constantly broadcasts its exact position and the precise time. Your phone or GPS receiver picks up these signals and calculates its own distance from each satellite based on the minuscule time delay it takes for the signal to arrive. To pinpoint your location on Earth within a few meters, the system must account for effects predicted by both Einstein's special and general theories of relativity. The satellites are moving at high speeds relative to us on the surface, and they are in a weaker gravitational field. Both of these factors cause time on the satellites to pass at a slightly different rate than it does on Earth. If these tiny relativistic time distortions weren't factored into the calculations, the GPS system would accumulate errors of several miles per day, rendering it useless for navigation within minutes. The same fundamental physics that allows us to measure the expansion of the universe is what makes turn-by-turn directions on your phone possible. The techniques developed to filter noise and extract faint signals from astronomical data are the direct ancestors of the algorithms that keep your phone's GPS lock stable, even in a dense urban canyon where signals bounce off skyscrapers. The need for ever more stable atomic clocks for deep space navigation and radio astronomy is driving a revolution in timekeeping that will lead to the next generation of terrestrial navigation systems, promising centimeter-level accuracy for autonomous vehicles, advanced robotics, and the precise monitoring of tectonic plate movements that could provide earlier warnings for earthquakes. The quest to map the cosmos has, in turn, given us the tools to map our own world with breathtaking fidelity, weaving the science of the impossibly large directly into the fabric of our daily lives. For centuries, we envisioned our solar system as a place of serene, clockwork order, with planets gliding along pristine, unchanging orbits they've held since the moment of their birth. But this peaceful picture is being dramatically rewritten by a far more dynamic and violent story. A wealth of evidence now points to a tumultuous early history, a gravitational ballet where the giant planets Jupiter, Saturn, Uranus, and Neptune underwent a grand migration, shifting their positions dramatically from where they first formed. This concept, known as the Nice model, named after the city in France where it was developed, suggests our solar system looked nothing like it does today for hundreds of millions of years after its creation. The clues for this great migration are etched into the solar system's architecture. The most compelling evidence comes from the Kuiper belt, that vast disk of icy bodies beyond Neptune. Its outer edge is unexpectedly sharp, as if something sheared it off, and the orbits of countless objects within it are clustered in specific, resonant patterns that can only be explained by the gentle, sweeping gravitational influence of a slowly migrating Neptune. Furthermore, the existence of the asteroid belt between Mars and Jupiter, with its strange mix of rocky and icy bodies, makes little sense unless Jupiter moved inward first, scattering material in its wake before reversing course and moving back out to its current position. This planetary dance would have sent a cataclysmic shower of comets and asteroids hurtling into the inner solar system, a period of violent bombardment that may have delivered water to a young, dry Earth and perhaps even seeded the building blocks of life itself. This revolutionary understanding completely reshapes our view of planetary formation and stability. It tells us that solar systems are not static, they are dynamic, chaotic, and can undergo profound reorganizations long after their host star has ignited. A planet's current orbit is not necessarily its birthplace. This knowledge forces us to reconsider the very definition of a habitable zone. A world could form in a perfectly temperate location, only to be flung inward into a scorching hell or outward into a frozen abyss by the gravitational interactions of migrating giants. The long-term stability we enjoy on Earth might not be the cosmic norm, but a fortunate and perhaps temporary alignment of circumstances. The implications for Earth's own long-term future are both sobering and complex. Our current stable configuration is the result of that ancient migration settling into a harmonious rhythm. But could it happen again? While the major migration event is over, the subtle gravitational tugs between planets continue. Over billions of years, these tiny interactions can lead to significant orbital changes through a process called chaotic diffusion. While the chances of a sudden, catastrophic shift are incredibly low, the solar system's history teaches us that nothing is permanently fixed. This understanding adds a new layer to our models of Earth's climatic future, reminding us that on geological timescales, even the shape of our orbit and the tilt of our axis are subject to slow change, influenced by the distant gravitational pull of the gas giants. Our planet's habitability is not just about the atmosphere we create. It is also intertwined with the silent, slow-motion dance of the planets, a dance that began with a violent migration and continues to this day. But perhaps one of the most personal and immediate returns on our investment in space exploration comes from a field that touches every single one of us: medicine. The human body is a product of millions of years of evolution, perfectly adapted to a life lived in Earth's relentless gravity. Take that force away, and the entire system, from our bones and muscles to our cells and immune system, behaves in unexpected ways. While these changes present a significant challenge for astronaut health, they also provide scientists with a powerful, unique laboratory to study human biology. By observing what goes wrong in microgravity, we gain profound insights into how things work correctly here on Earth, leading to medical breakthroughs that are already saving lives and rewriting our understanding of disease and aging. Consider the problem of bone loss. On Earth, our skeletons are constantly being remodeled. Cells called osteoblasts build new bone, while osteoclasts break it down. The mechanical stress of bearing weight and moving against gravity is the primary signal that tells our body to keep building. In the weightlessness of space, that signal vanishes. Astronauts can lose up to 1 to 2% of their bone density every single month, a condition that mirrors osteoporosis but at a dramatically accelerated rate. This isn't just a concern for long-duration missions, it's a perfect accelerated model for studying the disease itself. Pharmaceutical companies are now testing new osteoporosis drugs aboard the International Space Station. They can observe how effectively a new treatment counteracts bone loss in astronauts over a 6-month period, a process that would take years to study in elderly patients on Earth. This rapid testing in microgravity is dramatically speeding up the development of more effective treatments for the millions of people suffering from bone degradation back home. The revelations extend far beyond the skeleton. Without gravity pulling fluids downward, astronauts experience a fluid shift toward their upper body and head. This mimics conditions like hypertension and can cause changes in vision due to increased pressure on the optic nerve. Studying this phenomenon gives cardiologists and neurologists a new window into the causes and potential treatments for conditions like glaucoma and idiopathic intracranial hypertension here on Earth. Furthermore, scientists have discovered that microgravity causes changes in gene expression and alters the behavior of immune cells, often making them less effective. This has led to startling discoveries about how our immune system functions when the constant background stress of gravity is removed, providing new clues in the fight against autoimmune diseases and even improving vaccine development. Some of the most promising research is happening at the cellular level. The growth of protein crystals for drug design, which we touched on earlier, is just one example. Another involves studying the microbes that hitch a ride with astronauts. In space, some bacteria, like Salmonella, become more virulent and resistant to antibiotics. By figuring out what genetic switches are flipped in microgravity, scientists are uncovering entirely new pathways to target with next-generation antibiotics. This research is a race against the evolution of superbugs, and the space station is providing a unique arena to outsmart them. The field of space medicine transforms the human body itself into the most sensitive instrument aboard the spacecraft, and every heartbeat, blood sample, and cellular change recorded in orbit is adding a new piece to the complex puzzle of human health, delivering benefits that resonate in hospitals and clinics across our planet. For most of human history, astronomy was a silent movie. We could watch the universe, but we couldn't hear it or feel it. we were limited to the narrow band of the electromagnetic spectrum that our eyes could see, and later the radio waves, X-rays, and gamma rays our instruments could detect. But light can only tell us so much. It can be obscured by cosmic dust, distorted by gravity, or simply too faint by the time it reaches us. We were missing the full symphony of the cosmos, experiencing only a single instrument. That all changed with the dawn of multimessenger astronomy, a revolutionary approach that doesn't just look at the universe, but listens to it and feels its most elusive particles, combining these signals to create the most complete picture of cosmic events we have ever had. This new era began in earnest with the first detection of gravitational waves in 2015, which gave us ears to hear the ripples in space-time. Then, in 2017, it truly came of age when observatories around the world witnessed a single, cataclysmic event through multiple messengers. The gravitational wave detectors LIGO and Virgo felt the telltale chirp of two neutron stars colliding. Just moments later, NASA's Fermi Gamma Ray Space Telescope saw a brilliant flash of gamma rays from the same patch of sky. This dual signal set off the largest astronomical treasure hunt in history. Telescopes across the globe and in space swiveled to focus on that single point, capturing the event in every wavelength of light, from radio waves to X-rays. For the first time, we didn't just theorize about what happens when dead stars smash together. We witnessed it in vivid, multi-sensory detail. The power of this approach lies in the unique story each messenger tells. Gravitational waves provide a direct measure of the event's dynamics, the masses of the objects involved, their spin, and the final moments before they merge. They arrive at Earth instantaneously, acting as an early warning system that points our telescopes in the right direction. The light that follows, however, is where the real forensic investigation begins. The specific colors and intensities of that light, the afterglow of the collision, reveal the composition of the material ejected from the merger. It was by analyzing this light that astronomers confirmed the long-held hypothesis that such events are the primary cosmic forges for heavy elements like gold, platinum, and uranium. We watched the universe create the very elements that make up our jewelry and power our nuclear reactors. But the symphony doesn't end there. The third messenger, neutrinos, are ghostly, nearly massless particles that rarely interact with matter. Trillions pass through your body every second without a trace. Detecting neutrinos from a cosmic event is incredibly difficult, but it offers a priceless view directly into the engine of the explosion itself. Unlike light, which is created at the surface of an event and can be delayed or obscured, neutrinos are produced in the chaotic core and flee the scene at nearly the speed of light, bringing a pure, unaltered message from the heart of the cataclysm. By combining the gravitational wave signal that tells us how it happened, the light that shows us what was made, and the neutrinos that tell us what it was like deep inside, we can reconstruct a cosmic event with a level of detail that was pure fantasy just a decade ago. The implications of this new observational power are transforming our understanding of the most violent events in the universe. It allows us to rigorously test Einstein's theory of general relativity under the most extreme conditions, to understand the properties of matter at densities far beyond anything we can create in a lab, and to measure the expansion rate of the universe in a completely new and independent way. Each multimessenger event is a natural laboratory for fundamental physics, allowing us to conduct experiments on a galactic scale. Furthermore, the global collaboration required with physicists, astronomers, and engineers from dozens of countries and hundreds of institutions working in lockstep showcases a new model of scientific discovery, one that is open, rapid, and breathtakingly unified in its pursuit of knowledge. This holistic way of seeing the universe doesn't just satisfy our curiosity, it also sharpens our ability to understand and predict events that could affect Earth. By building a complete picture of how stellar explosions and collisions work, we improve our models of their potential threats, such as gamma-ray bursts. The technology developed to correlate these incredibly faint and fast signals is already finding uses in other fields, from improving global communication networks to creating new types of medical imaging that can detect multiple signals within the body simultaneously. Multimessenger astronomy is more than a new tool. It is a fundamental shift in our relationship with the cosmos, allowing us to experience its most dramatic stories with all of our senses at once, and in doing so, uncovering the physical secrets that bind the entire universe together. And so, as our journey through these 30 revelations comes to a close, we're left not with a simple list of facts, but with a profound new perspective. We began by looking outward to the hidden waters of Mars and the atmospheres of distant exoplanets, yet we found that every discovery, no matter how far-flung, ultimately circles back to us, to our planet, and to our future. These aren't just isolated scientific curiosities, they are interconnected pieces of a grand puzzle, revealing a universe that is actively engaged in a silent dialogue with life on Earth. The same principles that govern the formation of a cloud on Titan can refine our climate models. The brutal radiation that challenges astronauts in orbit is leading to new cancer therapies in our hospitals. The quest to grow food on the moon is revolutionizing agriculture in our deserts. This is the true power of space exploration, its unparalleled ability to serve as a catalyst for innovation. It pushes our technology, our biology, and our very understanding of physics to their absolute limits, forcing breakthroughs that would have taken generations to achieve if we had remained solely focused on terrestrial problems. The challenges of surviving in the void have gifted us with tools to thrive on Earth, from unbreakable quantum encryption and precise medical scanners to the promise of limitless clean energy beamed from orbital power stations. We set out to conquer other worlds, and in doing so, we learned how to be better stewards of our own. Perhaps the most transformative lesson, however, is the shift in consciousness it inspires. By confirming that the building blocks of life are scattered across the solar system, embedded in asteroids and potentially thriving in alien oceans, we are humbled. We are forced to see Earth not as a solitary oasis, but as a participant in a vast, interconnected cosmic ecosystem. This knowledge carries with it a dual responsibility, a duty to protect our fragile home with newfound urgency, and an inspiring mandate to continue reaching out to learn and to grow. The story these discoveries tell is one of incredible potential. They sketch the blueprint for a future where energy scarcity is a forgotten concept, where diseases are diagnosed and treated with unprecedented precision, and where our global society is secured against threats from both Earth and space. They invite us to envision a tomorrow where humanity is no longer confined to a single planet, but is actively shaping its destiny among the stars, using the limitless resources of the solar system to build a brighter civilization for all. This is more than just science, it is the next chapter of the human story. It's a narrative of curiosity, resilience, and hope, and it's a story that is still being written. If you've enjoyed this glimpse into the discoveries that are quietly changing our world, consider subscribing to the channel. Together, we can continue to unravel the universe's deepest mysteries, one cosmic revelation at a time.